Two slits are separated by a distance of 0.112 millimeters. Okay, so that is, in this equation, that's our little d. Okay, it's also the d in this guy too. So d is equal to 0.112 times 10 to the minus third meters, and that's because it's millimeters, right? Okay, are illuminated by 512 nanometer light, so our lambda is 512 times 10 to the minus ninth meters. Okay, let's see. And the interference pattern falls on a screen that's 4.8 meters away. Whoop. Okay, and that's this big D in this equation. That's 4.8. Okay. What distance separates the fringes on the screen? Well, that's just this. Okay, so let's figure it out, right? Okay, so S is going to be lambda, which is 512 times 10 to the minus ninth meters, times the distance to the screen, which is 4.8 meters, all divided by the slit separation, which is 0. to the minus third. All right, this this requires the use of a calculator. Okay, so 512 times 10 to the minus ninth times 4.8 divided by 0.112 times 10 to the minus third. And I'm getting that it's 0.0219 meters. And the next digit's a 4, like 42 or something like that, right? So that would be 2.19 centimeters. Okay. Now, let's imagine that you don't like this approximate formula because it does use, a few approximations, right? We could use this. We could find that. So let's take a look at this guy. So we've got a screen that's 4.8 meters away. We've got this these narrow slits, right? They're very narrow slits, and they're separated by a distance of 0.112, right? That's this distance between here and here. Okay, and what's going on here is we've got a central bright spot right there. Okay, and then we've got a maximum here, and then another one there, and another one there. Okay, and then what we're looking for really is this if we wanted to find this the legitimate way, right? We'd be looking at this triangle here. So let's imagine that I can draw a straight line. Let's imagine that that's a straight line between there and there. Okay, to really define that thing, we need to find the angle properly like this, right? So we're just going to make this we're going to make n be 1, right? This is n is 1, this is n is 2, this is n is 3. There's going to be a series of dots out here of constructive interference, and that's what this is finding. Okay, by the way, if you want the destructive interference, you're going to go n plus 1/2 times lambda, right? But okay, so what we're going to do here is put a 1 in there. We're going to go 512 times 10 to the minus ninth is 0.112 times 10 to the minus third sine of theta. Whoops, theta got all cut off there, but anyway, there it is, right? So if you do this, you can find theta, and I'll find theta here in degrees. So it's going to be the inverse sine of this, so 1 times 512, e to the negative 9 divided by 0.112 times 10 to the minus third, and that angle is, this angle here is 0.2619 degrees. And then I can find this distance here legitimately by doing something with tangent, right? We know that the adjacent side is 4.8 meters, right? And we know that the opposite side is, well, let's see, let's see, tangent of theta is opposite over adjacent, right? So therefore, the opposite side is the adjacent times the tangent of that angle, okay? So I can go 4.8 meters times the tangent of that, right? 4.8 times the tangent of 0.2619 degrees. I can do this. Okay, so 4.8 times the tangent of that angle I just got. And indeed I get, for this distance here, I get the opposite side is 0.0219. The next digit's a 4. It's a slightly different number from the approximate formula. But for these types of things, it's good enough, okay? So we've done number 1 2 different ways, right? Let's do number 2, which I'll show you that 2 different ways too. I'll show you the best way first, and you can just stop watching. All right, erasing. All right, so what is the angle? Let's do the best way. The best way is just using n lambda is d sine theta. Right, so the central maximum and the third order maximum. Okay, we can do this. The central maximum, by the way, is going to be 0 degrees. It's going to be right in the center. Okay, and then we're going to find the third order maximum, which that shouldn't be too hard, right? Okay, so let's see. So we're going to, if it's the third order, we're going to put a 3 in there, and then 512 times 10 to the minus 9th equals d, which is 0.112 times 10 to the minus 3rd times the sine of the angle. All right, so we're going to do the inverse sine of this times this divided by this. Second sine of 3 times 512 divided by 0.112 e minus 3. And I'm getting that, oh, okay, so the angle I'm getting is 0.7857. That's kind of fun, huh? Is there another way to do that? Well, there sure is, right? We can do an approximation, right? Let's imagine you're in a hurry. Okay, we know that it's 2.19 centimeters, right? So the third order maximum, so the distance separating the bright dots on the screen, let's draw a picture of this, right? There's a central maximum, right? And then there's a bright spot here. This is the first order, second order, third order, right? Okay, we know that this is 2.19 centimeters. So the third one is going to be 3 times that, right? So let's find that number. Where's that number? Okay, so 0.219 times 3. I'm taking the unrounded number in my calculator. We know that this distance is 0.065828, right? So how do you figure this out? Well, we know that this side here is 4.8, right? And you can either do the inverse tangent, right? Tan minus 1 of I don't know if this is any easier, right? You can also, by the way, just find the angle in radians, convert it to degrees, but I don't even know if that's easier, right? It's just going to be the inverse tangent of that. So second tan, that value divided by 4.8. Hey, look at that. I get the same thing. I get 0.7857 degrees. All right. Lots of ways to do these.